Zeal Education Society, redefining excellence.
Hello students, in the previous video lecture of basic electrical engineering, we have learned the numerical base on parallel plate capacitor, finding the electric flux, flux density, potential gradient, and relative permittivity. The expression for capacitance of parallel plate capacitor is C equal to epsilon 0 epsilon R A upon T. Indicate that the capacitance is directly proportional to relative permittivity and area of plate, and inversely proportional to thickness of the dielectric material. Lesser the thickness, higher will be the capacitance. Higher the plate area, higher will be the capacitance. Higher the value of relative permittivity, higher the value of capacitance. From this expression, we can write the expression, say like this: capacitance C equal to epsilon 0 epsilon R A epsilon 0 A upon D upon epsilon R, and from that we can write for the composite material. Now in this video lecture, we are going to learn the capacitors in series. Let us consider the circuit, three capacitors connected in series. C1, C2, C3, and the charge on each capacitor is same, plus plus plus. Charge is Q. Now in let us consider the three capacitors having capacitances C1, C2, C3 as shown in the figure. Let C1, C2 and C3 are the capacitances of capacitors and Phi1, Phi2 and Phi3 are the potential difference PD of respective capacitors. C is the equivalent capacitor, equivalent capacitance. Phi supply voltage. For series circuit, charge on each capacitor remains same. Charge on each capacitor same. Then PD across each capacitance is different. Potential difference across each capacitance or capacitor is different. Then third point, sum of individual PD across each capacitor equal to supply voltage. So Phi equal to Phi1 plus Phi2 plus Phi3. Also Q equal to C Phi equal to C1 Phi1 equal to C2 Phi2. Now Q equal to CV, and therefore V equal to Q upon C. Now, similarly, V1 equal to Q upon C1. V1 equal to Q upon C1, V2 equal to Q upon C2, V3 equal to Q upon C3. So this is 1, this is equation 2. Now putting the values of equation 2 in equation 1. Therefore, putting equation 2 in equation 1, Q upon C equal to Q upon C1 plus Q upon C2 plus Q upon C3. Therefore, Q upon 1 upon C equal to Q 1 upon C1 plus 1 upon C2 plus 1 upon C3. Therefore, QQ will get cancelled. 1 upon C equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3. This is the expression for equivalent capacitance of the capacitor. Now, if there are only two capacitors, if there are only two capacitors connected in series, then their equivalent C equal to C1 C2 upon C1 plus C2. Now from equation 2, IMP note, from equation 2, the voltage across each capacitor is inversely proportional to its capacitance, or PD across each capacitor is inversely proportional to their capacitance. That is, lesser the value of capacitance, higher will be the potential drop across that capacitor. Lesser the value of capacitance, higher will be PD across the capacitor, and vice versa. And vice versa. Capacitors in parallel. Capacitors in parallel. Let us consider the three capacitors having their capacitances C1, C2, C3, C1, C2 and C3 connected in parallel across this voltage V. This is the positive plate, this is positive plate, this is positive plate. And charge on each capacitor is different. This is Q1, Q2, Q3, and this is the total charge Q. Now in parallel circuit, charge on each capacitor is different. Charge on each capacitor charge on each capacitor is different. Then PD across each capacitor is equal to supply voltage. Third, total charge Q equal to Q1 plus Q2 plus Q3. These are the some salient features of the parallel circuit. Now say let three capacitors having capacitances having capacitances C1, C2, C3 are connected in parallel across supply voltage V. Let Q1, Q2, Q3 are the charges on the capacitors respectively, and C equivalent capacitance of parallel combination. Now we know that Q equal to CV. Q equal to CV and Q1 equal to C1 Phi1 equal to C1 Phi. Q2 equal to C2 Phi2 equal to C2 Phi. Q3 equal to C3 Phi3 equal to C3 Phi. Equation 2 as P equal to Phi1 equal to Phi2 equal to Phi3 in parallel circuit. See here we can PD across each capacitor is equal and equal to supply voltage, that is P equal to V1 equal to V2 equal to V3. Okay. So in this way, now let us put the equation 2 in equation 1. Putting equation 2 in equation 1 we have Q equal to CV equal to C1 phi plus C2 phi plus C3 phi. CV equal to phi common C1 plus C2 plus C3. PV will get cancelled and therefore C equal to C1 plus C2 plus C3. This is the expression for equivalent capacitance when the capacitors are connected in parallel. That means when the capacitors are connected in parallel, their capacitances get added. Added. From equation 2, from equation 2, from equation 2, the charge on each capacitor is different and the charge is directly proportional to charge on individual capacitor is directly proportional to their capacitance. Charge on each capacitor is directly proportional to the capacitance. So Q1 proportional to C1, Q2 proportional to C2, and Q3 proportional to C3. Higher the value of capacitance, higher will be the charge on capacitor. That is, higher the value of capacitance, higher will be charge on capacitor and vice versa. So, in this way, in this video lecture, we have learned the capacitors in series and capacitance in parallel, their salient features of the series circuit and parallel circuit, then the equivalent capacitance of the series circuit and equivalent capacitance of the parallel circuit. In series circuit, the PD across each capacitor is different, whereas in parallel circuit, charge on each capacitor is different and voltage across each capacitor is equal and that is equal to supply voltage. So we will stop here.